So this problem asks you to assign absolute configuration for these carbon centers, the chirality centers. So when you're given a problem like this, it is a good idea to draw the groups in their expanded form, so you can decide which one is higher priority and which one is lower priority. So this one has a phenyl group, like that. It has a hydrogen projected towards the viewer, and this one has a deuterium that is going behind, and here you have a CH3 and a sulfur and an oxygen. Okay, so on the left hand side, what I would say is, since the fourth priority is coming towards you, switch it so it's easier. So make this a hydrogen and make this a deuterium, and whatever configuration you get, just switch it. So now we have to assign priority. So this is a carbon with the chirality center. There's a carbon here and there's a carbon there. Between those two carbons there's a tie. Now what you need to do is look at what the carbons are attached to. So this carbon is attached to 1, 2 and 3 carbons. So this carbon is attached to 3 carbons. So let's say 3 carbons on this side. Whereas this carbon is attached to a carbon but a sulfur and an oxygen. Therefore this is going to be priority 1 as long as this chirality center is concerned. This is priority 2, deuterium is priority 3, and the hydrogen here is priority 4. So 1, 2, 3 counterclockwise, and since we just switched the groups, this is going to be an R. Okay, alright, so now let's erase the assignment here. So now on this carbon, sulfur is the highest priority, next oxygen is second highest priority, this carbon is third priority because the carbon is attached to a bulky phenyl ring, whereas this carbon is only attached to 3 other hydrogens. Therefore this is third priority, and this is the fourth priority. Since it's pointed away, it's easy to see what's going on here. So 1, 2, 3 clockwise, and therefore this is also an R configuration. So it is simply just finding out what the absolute configurations are and check your answer. So option A is going to be the right answer here. Okay. For this one, which is the enantiomer of the given compound? So we are given a Newman projection, and we should find out what the priorities are based on this. Okay, so this problem I think is fairly easy because if you look at the Newman projection, let me redraw it here. OH, CH2Br, and then CH2OH. On the carbon atom in the back, you have a CH3 and 2 hydrogens. So which means that the carbon on the back is not a chirality center. Okay, we have only one chirality center here. So oxygen, carbon, carbon. So this is highest priority. This is a carbon, that's a carbon. You also have a carbon on the back. Okay, but this one is attached to a bromine, so this is second highest priority. This one is attached to an oxygen, so third priority, and the carbon on the back is your fourth priority. So since the carbon on the back is already pointed away, you simply have to see whether this is clockwise or anti-clockwise the way it is here right now. So 1, 2 and 3, this is an clockwise rotation, therefore this is an R center for that carbon atom. Okay, alright, so that's an R. Now if you look at the 4 options here, they're all going to be in Newman projection, so in Sawhorse notation. Okay, so now we had to find out which of these is going to be the S enantiomer. So this is 1, this is 2, that is 3. So if you're standing here, this is going to be 1, your CH2Br is going to be on the right, this is going to be on the left. So this is a clockwise as you are looking at it from this angle. Okay, so this is an R molecule as well. Okay, and here if you look at it from this angle here, 1, 2, 3. So again from this angle, this is going to be a clockwise rotation. So this is also an R molecule. Okay, now if you look at it from again this angle here, number 1 is this oxygen group, and then number 2 is the CH2Br, number 3 is on the top. So this is to the right, this is to the left, and 3 is on the top. So this is also going to be a clockwise rotation seen from this angle. So this is also an R molecule. Okay. So if you look at this molecule, priority 1, priority 2, and then priority 3. Therefore, this is going to be counterclockwise and seen from this angle. Therefore, this is the S center, which is the enantiomer of this compound. So that makes it option D. So in this problem, we need to find out in the given Newman projections, right, which one represents the most stable conformation for this given structure here. Okay, so it's dimethyl, or sorry, it's going to be 1, 2, 3, 4 dimethyl butane. Okay, butane, it's going to be that structure. All right, so they're all dimethyl butanes, so you don't have to really check if they are dimethyl butanes, so that is fine. We just have to see which of these is the Newman projection that represents the most stable conformation. Okay, most stable meaning the one that's going to have the least steric hindrance. Okay, if you look at this structure here, methyls, there are 1, 2, 3, 4, there are 4 methyl groups, right, and they're all really close to each other. Methyl 1, methyl 2, methyl 3, methyl 4, so they're all really close to each other. You can see here. All right, here if you see, there are 3 methyl groups that are close to each other, and this methyl is staying away, so 3 methyl groups next to each other. Here you have 2 methyl groups really next to each other, and really next to each other for on the other side 2 methyl groups. Okay, here also you have 3 methyl groups close to each other and 1 methyl groups away from each other. So this one is going to be the most stable because there is more space between the methyl groups on one side versus the other side. So that's how simply you can interpret this problem. Okay, because you have 3 of them close to each other, this one is going to be, these 2 are going to be the same energy because 3 of them are next to each other, 3 of them are next to each other. In fact, you take this conformation and just turn it around a little bit, you will get the same conformation here. These 2 are the same. This one is going to be the least conformation because there is so much free space here, and all the methyl groups are cluttered next to each other over there. So option C is the right answer. So which compound will have 3 peaks of equal height and 3 values of equal depths? So which means we are looking at something like this. Like that, right? Of equal height and equal depth. Okay. So there is no difference between the energy of the staggered and the eclipse conformations. There is only one staggered and one eclipse conformation in this molecule. So which compound is going to be that? So let's take for example option A and see how that looks. So if you take 1,2-dichloroethane, the molecule is going to look like this. So you have chlorine, for example, chlorine here, sorry, hydrogen here, and a hydrogen over there. And if you want to start with the eclipse conformation, that is going to be a hydrogen there, a chlorine here, and a hydrogen there, let's say, right? So if you now draw the Newman projection for this, say you're standing here looking at the molecule, then it's going to be an inverted Y, sorry, it's going to be a Y both on the front and the back, and then you have the chlorine here on the left, hydrogen on the right, hydrogen here, and a chlorine on the back here, a hydrogen here, and a hydrogen here. So now if you go to a staggered conformation, let's say, you will be able to get this. So if you rotate the bond on the front, okay, you have your hydrogen here, chlorine here, chlorine here, and the hydrogens. Now the next eclipse conformation you get is going to look like this. Chlorine, hydrogen. Next eclipse conformation you get, chlorine is going to be here, there is a hydrogen here, and that's a hydrogen here. Now, sorry, like that. Now this eclipse conformation and this eclipse conformation, they are not the same, because this one is going to have lower energy compared to this, because the two large chlorines are next to each other. So as long as you have three groups in the front that are different, you are going to have different energies. Okay, so therefore this one is not going to have an energy diagram that looks like this. Same story here, because these two chlorines are the same, whereas this hydrogen is different. Once the chlorine gets close to this chlorine, it's going to have a different energy compared to the chlorine getting close to this hydrogen. So that means option B is going to be the only right answer, because no matter what you do, the front carbon is always going to have 3 bromines, and the back carbon, no matter what you rotate it into, it's going to have only one eclipsed and one staggered conformation. So let's quickly look at that. So if you look at option B, then on the front you're going to have bromine, on the back you have one chlorine and 2 hydrogens, and no matter what staggered conformation you get from here, they're all going to have the exact same energy, because they will always be next to 2 bromine atoms wherever you look. Therefore option B is going to be the only right answer.